Welcome to another session. In this parametric tutorial, we are going to look at the parametric model of Gherkin, which is developed by Foster and Partners. I'll quickly show you what the tower looks like. It's basically a circular structure that has some sort of continuous form, and it's having this type of digrid structure on it with triangles. So I'll be using Lunchbox tools for this exercise. So we'll be just developing kind of an approach using Lunchbox tools for the structure, for the diamond structure of the tower. And on the channel I also have another video where I cover some of the surface division tools for Lunchbox. You can also check that out. But for this exercise we'll be essentially looking at how we can develop panels on a surface. So I already developed the script here, which I'll show you. This will be the outcome of the script, and we're going to build it from scratch. But basically the idea is that we are working with these diamond panels and we are giving it some sort of thickness or depth, right? So that we are mimicking almost the helical movement of the Gherkin. So I'm going to start building this from scratch. So I'll just create a new sketch and I'll just delete these forms. So we start from the beginning. So the first thing we're going to do is develop the parametric form of the tower. And for that one, I'm going to create a bunch of circles. The Gherkin plan being the continuous form. So basically, we want, let's say, a level. Let's say the floor height is 3 meters and we want 20 floors. Then I can create an XY plane, XYZ point first. So we construct a point with the Z, and then I create an XY plane on these points. And let's start with the simple circles on these planes. So these will be the radii. Let's say our radius is 30. 30 is too big. Rounded up to, let's say, around 10 or 12. I think 10 will be fine. I think we have more floors and the dimensions will be a bit different, but I'm just trying to approximate the proportions of the towers to see how the Lunchbox tools would work. So the next step is to actually give the curvature. We know that so the tower has this sort of shape. Let me actually see. We have kind of a curvilinear shape that's tapering to the top. So we're going to do a graph mapper, and then I'll have the range here. And if I connect the range, this will output 21 values. This outputs 20, so I'm going to just subtract 1 from the series, and let's make this with a Bezier type of section. And all I have to do is multiply this outcome with this radii and change the circle. So this was, this is somehow, we can try to find the form of the Gherkin. So we want, let's say, the maximum radius towards the base, or maybe somewhat of a curve here as well. And then we want it to taper something like this, right? So it's going to be kind of having a belly towards the middle. You can try optimizing it a bunch of ways, but that's basically the essence of the form. So I'm going to diminish it a bit as well. So that's the shape. Then we want to loft these circles so we get to the final surface for the tower. So that will be the first part of the script basically. So for this exercise I'm going to use the diamond panels, but you can also check out some of the other paneling tools like the skewed panels and change the U and V numeric count, and you would get different numbers of panels. So depending on the type of shape you want to use, the type of panels might be changing. Maybe these are twisting as well, maybe your circles are twisting. However you want to define it. You can also try out hexagon cells, but we're going to do this exercise with the diamond panels. So I'm going to create the diamond panels, and let's plug in some some parameters for the UNV so that we look at these panels. So now this output actually gives me two sets of surfaces: the diagonal panels, which are made out of quads with 4 vertices on the corners, and then we have the triangles. Now the Lunchbox tool doesn't recognize if your surface is revolving, so we have in this case these special triangles here that are trying to close, because that's the center of the revolution. So we need a second method to actually combine these, which I'll get to on the second part of the video. So the first part is trying to basically give these panels some thickness. So the way we can do that is by extracting the surface normals out of the surface. So one way of doing it, or the usual way I use, is getting the centroid of the surface panels, which will give you, which you can use the area and it will give you a centroid of the panel. Then you want to actually find a normal direction for this surface. So that would be basically perpendicular to the surface. Now you can get this a bunch of ways. You can actually get it directly from the panel, but if the panel is somehow distorted, then that normal direction could be facing a different direction. I would always do it from the base surface. So you need to use the base surface, the lofted surface. And what you need to do is first find the surface closest point. So we want to find where this point is on the surface. So I want to get the surface and look for the closest point. You can see that there is some sort of deviation, right? Because the panels are somehow offset from the surface. Then using this evaluation, it gives you a UNV parameter. Then you can evaluate the surface at that UNV parameter, and we are still evaluating the base surface. And that will give you these planes. And those planes are basically how we can move geometry on the surface. So we can actually get the normals of the surface as well. And those normals are actually here. So if I do vector display to check out these normals, and I want to anchor them to the surface itself, let's actually hide this. And these are the offset directions that you can find that are perpendicular to the surface. So all these arrows are perpendicular to the surface, and this is really important, because if these are not perpendicular, then we cannot have this type of chamfering effect for the panels. The next phase is actually, there's another tool here under Lunchbox. If you go to generate, there's a panel frame. We can use the panel frame. So I want to, let's say, develop a panel frame for these panels. That already gives me a frame and a panel, and it also uses a coefficient. So here, let's place in a number slider. Let's make this, let's say it is 0.64. Now this plane, this frame, if I bake it, you will see that the frame is actually flat. So if I bake this, you will see that that plane is flat. So it doesn't have the thickness, the depth that we want, because it's directly trying to offset the boundary, and that's not what we want. We want to have some depth for the structure. So one way of achieving that would be to extract the wireframe of the inner panel, which is here. So this is the inner panel, and then we also have the outer panel, which is the surface itself. So I can move this panel frame, the surface, inward, right? So that's maybe something we can do. So if I want to move that inside, let's get the surface and move it. Well, how are we going to move it? We're going to use these vectors, right? So I can do vector amplitude to actually control the thickness of the offset, or the vector length for displacement. And I can associate some numeric value here, let's say 0.5. We can also preview what this vector looks like. So that will be the relocation vector. And if I reverse this, you would see that we want to move them inward, right? So we can reverse this vector, and it's now pointing inward. And if I take these surfaces and use these vectors, I can move those directly inside of the surface, and that's exactly where we want them to be. I'm going to hide this frame, and I'm going to hide the original surfaces because now they have been relocated. And for this guy, we can maybe get the wireframe out, right? Because we don't want to use it as a surface, but we want to get its wireframe. and we want to connect this wireframe to the moved surfaces wireframe, right? So we can get this guy out as well. So these two things, they will define, you can see that there's some already depth happening. We want to loft these two. And the data is the data is already grafted, so all I have to do is join these wires, and then I want to essentially loft these. So I often do a weave here so that we can put these into groups of 2, and then I can loft it, and you can see that these are the panels that I wanted. So if I hide everything else, and I also have the panel, I think, which is the outer panel. Let's hide that too. Let's hide the diamonds. Let's hide the base surface, and voila. Those are the offsetted diamond panels that we extracted from the surface. And that was actually easier with the Lunchbox tools, because if you want to develop these quad panels on the surface parametrically, maybe you want to change their interval or whatnot, then you have to evaluate each of these points and weave them together. So Lunchbox already gives you the diamond panels, but because our surface is revolving, we don't have these corner patches, right? Instead of diamonds there, we have 2 triangles, and those guys are located under the surface division. So when we first divided the surface using Lunchbox diamond tool, we got diamonds and we got triangles. So we need to somehow filter these triangles. So basically, this was actually a lot trickier than I expected it to be, because there is no simpler way of combining these surfaces. So one way I can approach it is you can do a boundary representation join, which will basically join some of these surfaces with each other. So if you bake it now, if you bake these surfaces, you will see that there are some triangles at the base, and these guys are now joined. So they shouldn't be triangles anymore, but they should be quads, or at least they could behave like quads. But they're also grouped up with triangles as well. So maybe we can filter them out. So one way of filtering them out would be to deconstruct the B-rep. So we can look for the vertex count, because if it's a quad, then it should have 4 vertices. If it's a triangle, it should have 3 vertices, right? So we can use this data to somehow filter it. And let's actually, I'm going to hide this loft as well so that we can concentrate on these triangles. And the way you can filter it, you can see that this list is outputting the number of vertices. And basically, we can do a list length here. We want to check how many points are there in these lists, right? So if you grab the panel, you can see that the first one is a quad, then there are triangles, and there are quads in there as well, and the data is somehow mixed up. And we can actually do, we can actually check for equality here. So if we want the quads out, then we want to check if the length is equal to 4, then it will give me a Boolean pattern. And we want to actually flatten this list. We don't want it to be grafted, so that we can have a single list. And you can see that initially, after we joined these surfaces, there were 29 surfaces, and there are untrimmed surfaces which are triangles, and there are open B-reps which are quads now. And our true-false pattern corresponds directly to that. So if I call pattern this and extract the surfaces, I only have quads now on my selection, and I can hide this, and now I have that zipper line where the surface is closing on itself. Now this part is a bit trickier, because if I were to directly extract the wireframe, let's say we want to extract the wireframe of these, you can see that because it's made out of 2 flat triangles, it's also giving me this line in the middle, and that's not what we want. So it doesn't give me a clear wireframe of the diamond. So we need to deconstruct the boundary representation again, so we can go through its corner vertices this time and make a polyline out of it. So I think we can also grab the area, which gives me the centroid, which is fine. And then for this boundary representation, we want to look at the vertices, and I can go through the vertices using list item. So I grab, let's say, up to 3. I want to grab these points. So this is the first point. First point is at the base of the diamond. Then the second point is moving to the top, actually. That's where it's not giving me a simple polyline. And the second point to the left and the third point to the right. So that's why the list is a bit mixed. And if you want to merge this data together, then I have to start with 0. Let's say I go to the left, which is item number 2, and then I want to go to the top, which is item number 1, and then I go to the right, which is item number 2. And that will give me 4 vertices now, and if I draw a polyline through these, that will give me the bounding shape, but it's not closed. So I right click here and set true so that the polylines are closed. Now I've converted the surfaces into quads, basically into diamond shapes, and now I can actually use it to do the same operation that I did for the diamond panels on top, and I can actually give them some thickness as well. So one way to do it would be, these are not surfaces, they're polylines, so maybe we can first scale them down where they are. So we can scale this geometry down using the centroids, and this data is grafted, this data is not. You can actually flatten this out so that we can have same data streams coming in. And here for the surface frame, I use this coefficient 0.64, which is the scale, so I can attach the same coefficient here for these panels as well. And what I want to do is find the vectors for these points as well. So find the vectors for these centroids. And how did we find them? I have the base surface here, which is the lofted surface, and I have a surface CP, surface close point, and evaluate surface functions here. So I'm just going to copy these two, bring them over here, and instead of using this point, I'm going to use the centroids here, and the surface would be identical. And for the vector, I can actually bring this portion as well. So vector amplitude, vector display, bring this part as well, and connect the vector and connect the anchor point here too. So let's see what they look like. They also point in the right direction with the right amount, right? So we evaluated the closest point on the surface for these quads, and we found the normal, and now I amplified it and I'm pointing it towards the inside, and I'm going to move the scaled version using this vector. So now it's displaced to the interior. So that's exactly where you want it to be. And the remaining part is pretty straightforward. So I want to weave this geometry with the boundary polyline, but in order to couple them up, we need to graft this data stream. So I grafted both of these, and then I loft this part, and voila, that was basically those are these triangles, right? So these panels. So we have these guys, these lofted surfaces coming in with the regular diamonds, and we have these coming in. I actually have like 2 triangles, one at the bottom and one on top, but you can delete them after you bake them as well. So that actually takes care of a lot of the operation. So you can just hide these, and that would be it. So let's see what happens when we bake it and do some topological distortion. So I'm going to move it around so you can see the geometry is fine. And in order for you to check that the offsets are in the same direction, you want to do a clipping plane, and you want to look for symmetry between these panels, right? So they should be identically scaled, and that's really important. So we can see that they're folding the right way. And if I move it up, that's going in the right direction. I'm not going to cover like how you're going to close the top or these panels with triangles or surfaces. You actually have the panels here too. Maybe you can check those out later. So this is actually working fine, and we can actually develop other types of shapes with this, and we can actually topologically customize it. We can actually increase the number of levels, maybe increase its height as well. So let's say we increase its height and increase its radius so it becomes a lot wider, and then we can also change the number count for the diamonds because our operations are scripted. Actually, this, when I make this even, it doesn't work. Let's try to make it. When it's odd, it doesn't work. This needs to be even. Just the V divisions need to be even, so that we have two panels here that could join. Otherwise, it doesn't recognize the join. And I'll bake this version as well, which is basically similar to the example I did, but you can see it's it can basically be parametrically altered. So that's actually proof of concept, right? So we built this object parametrically now. So that was it. I wanted to show you some of the Lunchbox tools, the panels, and maybe you can try a similar exercise using other types of divisions, other types of panels, or maybe you can check out the structure, but for the structure to work you need to add some profiles as well. I hope you like this content. So I'll see you guys next week with another session. Take care.